Okay, so today we're going to finish up on AVL trees and also talk about another balanced binary search tree called 2-3 trees. Remember that we are on Piazza here, so if you have any questions, go ahead and post there. Otherwise, yeah, we'll hope to get through balanced binary search trees today. As far as AVL trees go, remember that you insert just normally, and then you have these kind of rotations, a left rotation, right rotation, a left-right rotation, or right-left rotation. Searching, of course, is pretty straightforward. That's exactly the same as any other binary search tree. But deletion is a little tricky. Initially, it's the same thing as a binary search tree, but your deletion, a deletion, may cause the subtree to be unbalanced. So if it's unbalanced, right, first of all, you're never going to get a balance greater than 2 or less than -2. So it could unbalance it as 2, in which case it would be unbalanced to the, remember what we said last time, if it's positive, it's, here we go, it's unbalanced to the left, and if it's negative, it'll be unbalanced to the right. So you could, by deleting something, you could unbalance it left or right or something like that. And you have to go up to the parent where it's unbalanced, and then you have to rebalance it using the same 4 basic types of rotations. But think about that. That could cause yet another imbalance because what you're doing is you're necessarily decreasing the height of the tree. And if you're decreasing the height of the tree on one side, then that means that you're unbalancing it to the other side automatically. So, okay, fine, rebalance that. Well, now look up even higher, and you may have caused another imbalance. So essentially what you have to do is you have to rebalance all the way back potentially to the root, right? So a deletion may cause the subtree to become unbalanced. A rebalance, cascade, that's a good word, may propagate all the way back up to the root, right? That's okay. Each rebalance, that is rotation, is only order 1. Why? Because it's just a bunch of pointer reference changes, right? But but if you're doing that all the way back up to the root, then a deletion may end up being order D, where D is the depth of the tree or the height of the tree, either or, right? But since it is balanced, then D is going to be order log n. And so we're right back to perfect kind of order n for all operations. Insertion is going to be order n because it is proportional to the depth. The rotations, the rebalances, that all it all ensures that the depth, the height is going to be logarithmic. I've mapped out a worst case scenario example here. This is available in the book, by the way. Suppose that we delete 3, right? So 3 has been now blanked out here. And you can see that it becomes unbalanced to the right at 10. So what we need to do is we need to do a left rotation. When we do a left rotation, 12 comes up to be the new root of that subtree, and 10 goes down to be the new left child, 14 gets pulled up. That leads to something that looks like this, though. Right? And you'll see that we've unbalanced it yet again to the right because we've necessarily decreased the height of the left subtree with respect to 20. That's okay because we can do yet another rotation. Another rotation about 20, since it is unbalanced to the right because it's negative. What would that look like? We need to, do a left rotation here. So 30 comes up. Where does that subtree rooted at 25 end up being? Right child of 20. Right? There we go. And so we've rebalanced there. But necessarily by pulling this entire subtree up, right, we've decreased the height, and therefore we have unbalanced it at the root here. Now these are just generic trees here, T1 and T2, that are hanging off of there. So in this case, we're unbalanced to the right, and we're still unbalanced to the right with its right child, so we end up doing yet another left rotation. And 60 comes up to be the new root. T1 and T2 are hanging off of different nodes. Well, T1 is hanging off of a different node now. Okay? But this is a worst case scenario where you have to propagate it all the way up to the top. And this one particular example was skewed all the way to the left. So we were always doing left rotations here. You could have a combination of left-right rotations and the other two. Okay? So there is an example of a delete. And by the way, remember how we delete? I said that it was initially the same as a regular binary search tree. Remind me though, what is that? How do you do that with a regular binary search tree? What if it's a leaf? Then you just delete it. What if it has one child? And then you just promote that one child up, right? Here. So let's take a look at maybe some examples as a review here. So if it's a leaf, there's no, it's hanging off some parent here, and we're about to delete this node. Who cares, right? The parent now no longer has a left child or a right child or whatever. But what if it has a child? What if I want to delete this node right here, and it has a parent, and it has, say, a left child, but no right child? How do I delete X?
You promote the left child to
The left child of the parent, right? And right, and if it were a right child, then it would be the mirror image of this, right? No big deal there. This is just exactly like a linked list. But what if I have two children? Here's the parent, here's the left, here's the right. And let's suppose also that there's an entire tree hanging off of each one of these things. Right? Let me go ahead and we're going to delete X here, and it has a parent. So I want to delete X. Can I promote the left child? That'll end up having 3 children, right? This the subtrees that it already has, and then also R if I tried to promote L. If I tried to promote R, I would have the 2 subtrees that it already has, and L again. So that's not a binary tree. So how do I go about doing this?
first from the greater of left and rights and splitting it down.
Not all. Well, let's just jump all the way down to begin with and only exchange one node, right? So replace X with either the minimum element in the right tree or the maximum element in the left tree. All right? Maybe an example here. So do I have a binary search tree here? Maybe if I go to computer science 2.
So
There we go.
minimum element in the right tree or maximum element in the left tree.
Yep. So let's go with the first strategy. The minimum element in the right tree. In this case, say that I want to. Okay, there we go. Say that I want to delete 50. Let's delete it, but we don't want to lose the topology of this tree. What could I promote up to 50 so that this gap is taken care of, but also so that the binary search tree property is preserved? Again, could I promote up 40 up here? Well, if I did, then I'd have 20, 45, and 30, all of it as its children, right? And I can't have that. So what can I do? Let's go ahead and find the minimum in the right subtree. So here's the right subtree. What's the minimum among all these? 60. Right? So what if I promoted 60 up here, having deleted it? That would work, but now what do I have to do about 60? Well, there's no problem here, right? There's no left child. There is a right child, but we already took care of that with those 2 cases that we just mentioned. You just immediately promote it up. Okay? Let's take the other strategy. What if it's the maximum in the left subtree? So once again, let's delete 50. And what's the maximum in the left subtree now? Here's the left subtree. Where's the maximum? 49. Right. So let's promote 49 up here. And we have to delete 49. But that's again okay because it only has one child. Well, for this particular example it works, but could I come up with another example in which the maximum in the left subchild has 2 children? And paint myself into a corner? Let me go ahead and try that. Here's the max. And it has 2 children, L and R. Remember, it's a binary search tree. Can this happen? No, why not? What can you say about R? It's greater than max. So this is not the max. Right? You go down to the left subtree and then all the way right as much as you can to find the maximum, and it's guaranteed that there's not going to be a right subchild there. There might be a left subchild, in which case you know how to take care of that. Right? So all you have to do is promote up the maximum in the left or the minimum in the right, and then end up deleting that node that you used to replace it. Right? That's the regular binary search tree deletion operation. Now again, when you go over to AVL trees, it becomes more involved because then after this initial delete, you have to propagate your rebalancing potentially all the way back up. You could get lucky and it doesn't unbalance at all. Or you could have an unbalance, but then rebalance in the middle of a tree, and it's all balanced again now. You don't have to necessarily go up all the way to the root. Okay? All right. Any questions so far? Then let's talk about another type of tree. This is a very, very general B trees. Right? Don't ask me why they're B trees. But there are several authors that get credit for doing this. They came up with, the first author came up with what we'll actually talk about, 2-3 trees, and then other authors came along and they generalized it to these B trees. But basically the idea here is that nodes may contain more than one key. We're going to look at the general case, and then we're going to focus on the simple case so that we can actually visualize this stuff. Every node may have at most m children. Right? So this m here is a parameter that you can tune. Right? Every node except the root has at least m divided by 2 ceiling children. Right? So you have this range of children. You've got a node, and it could have anywhere between m divided by 2 children and m children, and it could be variable within that. The root has at least 2 children unless it's a leaf. Right? And that's just an edge case kind of definition. Okay. Non-leaf nodes with k children have k-1 keys. Now to visualize that, to understand that, if you have k children here, let me go ahead and I'll depict it as that's a node. I'll depict it as a long node because it has all these keys. Right? And we'll talk about the keys here in a second. What if I had this many children? 1, 2, 3, 4, 5 children. How many keys do I need to disambiguate which way you go if you're searching for something? I need a first key, key 1, to indicate that anything less than key 1 is you follow this path over here. I need another key, key 2, so that anything that is greater than key 1, or but less than key 2, you follow this. Right? Anything that is greater than key 2, but less than key 3, you follow this. And key 4 again. So if you've got m children, how many keys do you need? Or if you've got k keys, you can have k plus 1 children, or vice versa. The way that I put it before is that if you have k children, you have to have k-1 keys to know which child to go to if you're searching. And consequently, if you're inserting stuff or deleting stuff. Another condition is that all leaves have to appear at the same level, and they cannot be empty. All leaves are non-empty. Okay? By implication, all internal nodes are not going to be empty either. Right? We're going to focus on a special case here, the 2-3 trees, where m is equal to 3. By the way, if you take m is equal to 2, let's come up here and plug that in here. Every node may have at most 2 children. Sound familiar? Every node except the root node has at least m divided by 2, ceiling 1 child. Right? That's so you have between 1 and 2 children. Right? That's kind of a binary search tree, but you have this lower bound on the number of children. And non-leaf nodes with 2 children have 1 key. You go left or you go right. Right? So when m is equal to 2, then this is kind of like a binary search tree already. What about when it's 3? Right? With 3, you have 2 types of nodes. You have a node with either 1 key or 2 keys. Right? So let's come over here and look at this. This is what are they called again? They're 2 and 3 nodes? Yeah. A 2 node. So a 2 node, quote, quote, is a node with 1 key and both children. And so it's our regular idea of what a binary tree looks like, except for we have this new condition. We always have both children, okay? And this is over here, and this is over here. And this is less than k, and this is greater than k. And then we have the other type of node, a 3 node. Oops. 3 node is a node with 2 keys and 3 children. So what does that look like visually? Well, let's make it look nice. There we go. You have key 1 and key 2. And then you have exactly 3 children. 1, 2, and 3. And this child, this child, this child, they may have 1 or 2 keys. They might be 2 nodes or 3 nodes. It doesn't matter. Everything over here, and I'll annotate this, everything over here is less than key 1, excuse me. Everything over here is greater than key 2. And so therefore everything in between is less than, or let me rewrite it. Too big. There we go. Everything over here is between K1 and K2. So X is less than or equal to X and then X. There we go. In fact, I want to write it a little bit different here. So key 2 and then X. Where X is a node in this subtree over here, X is a node in the subtree or the subtree. Okay? So you have 1 nodes and you have 2 nodes and you have 3 nodes. Okay? So how do we go about inserting into these things? So again, you have a 2 node containing 1 key with 2 children, regular binary tree node. A 3 node containing 2 keys and 3 children because, you know, if you've got X sections, how do you cut them up? You need X minus 1 slices in order to cut those things up. And so it makes sense. What about insertion? Well, first of all, what about searching? How do you search?
Check all the keys starting from the root, right?
Yep, it's just a regular old search. But instead of going left or right, instead of just left, right, you go left or right, or center, or right. Right? So you just have one more key comparison if it's a 3 node. Right? Do I go that way, and do I go to the center one, or do I go to the left? And also, you're looking at the 2 keys in that 3 node. Is that the key that I'm searching for? Is that the key that I'm searching for? So you basically have 5 questions. Is the thing I'm searching for less, in which case I go left? Is the thing I'm searching for exactly equal to the first key, in which case I'm done? Does it lie between those 2 keys, in which case I go to the center? Is it equal to the second key, in which case I'm done again? And the last one is, do I go left because it's greater than both those keys? Yeah.
So is it more efficient because you're cutting out more space in the tree with every like step down you go? Or
It's efficient because the setup is going to ensure that the depth is logarithmic. And so everything is going to be order log n. That's the whole point of a balanced binary search tree. It's enforcing balance by making sure that that the tree is basically full, right? All the leaves are at the same level. Another question?
So just to clarify, the keys are themselves elements of the tree.
Yeah, you're searching for a key, yeah. And then that key is associated with some value that you're actually, key value kind of data structure.
Okay.
Right?
So all these trees are still balanced.
It's balanced because of the requirement that all leaves appear at the same net level and are non-empty. Right? And so we'll get to the math behind it here in a second, after we see a couple of examples. But first of all, we need to understand how to work with them, and then we'll go to a visualization tool here in a second. Oops, that's not what I wanted. What about insertion? Insertion in this case is always done as a leaf, just like a regular binary search tree, by the way. A regular binary search tree, when you insert something new, it's always going to end up as a leaf. Right? If it's a 2-node, if you insert into a 2-node, guess what? You've got room to grow. You can grow into a 3-node. If it's a 3-node, unfortunately, you don't have room to grow. You can't hold 3 keys. You can hold at most 2 keys. So what happens is you take and you arrange the keys, and you've got 3 keys here, and then you take the middle one and you promote it up to the parent. Now, the promotion may end up overflowing that key, or that node, and now it has 3 keys temporarily. That's okay. You keep promoting it up. When you promote something up, you split it out into 2 subnodes. Okay? So for example, let's go ahead and visualize this with, let's go ahead and use the tool. All right. Here we go. So what I want to do is I want to insert 8 into an initially empty tree. Oh, come on. That's all the button. All right, can we all see that now? Okay. All right, you might not be able to see it very well, but that's an 8, right? Now let's insert 4. What's going to happen here? That's a 2-node. It only has 1 key. So we can put that into that same node. That is the leaf, right? It's the root and it's the leaf because there's only 1 key in the tree. So it becomes a 3-node. And we arrange the keys 4, 8 because that's the order. But the second that I put in, say, 7, now it's going to be inserted in the same node, but we can't have 3 keys. So I'm going to arrange them 4, 7, and 8. What happens to that middle guy? That 7? It gets promoted. And we end up with a regular old binary tree. Right? Yeah?
Wait, so it seems like you were talking as if there were more nodes at some point than just the 4 and the 8.
Well, I mean, eventually, I'm going to continue here, if that's what you mean. Right. Let's continue. Let's insert, say, 2. Where is 2 going to get inserted? We're going to come down to 7. 2 is less than 7. So we go down to the left child, which is a 2-node, and it only has 1 key. So we have room to grow. And it ends up being a 3-node, 2 and 4. Okay? Let's insert one more thing. Say a 3. Right? Now, where is 3 going to go? It is less than 7, so it goes left. And that's the leaf, so that's where it gets inserted. 2, 3, and 4. But that's too full. Right? We can't hold 3 keys. We can only hold 2 keys. So 2, 3, 4. 3 gets promoted up to the parent. Now, when it gets promoted up to 7, right, is there room for it to place it? Yeah. Right? But what do the children look like? So maybe let's draw a temporary diagram of this thing. So 2, 3, and 4, right? And then it was 7, and what was it? 8. There we go. 8 over here. Now if I take 3 and promote it up to 7, what's it going to look like? 3, 7. And then 8 is still over here. Over here there was 2 and 4. But this is a 3 node. It has to have how many children? 1, 2, 3. That's okay. You promoted 3 up here, meaning that you end up splitting this thing in half. All right? And so what's it going to look like? 3 and 7 up here. And then 3 children, 2, 4, and 8. Cool? Let's find out what it looks like. 3 gets inserted, promoted up, and then you split that node. Okay? Let's do some more. Yeah, go ahead.
So the root node is a 3 node now, right?
It is a 3 node now with three children and 2 keys.
Wasn't the one on the left when it had all 3 there? Wasn't that like a 4 node?
Temporarily, but we're not done with the insertion operation, right? We find that it's too full. I mean, in an actual implementation, you might allow some overflow and then correct for it, or you might just hold it into a temporary variable over here. I can't fit it, so now I need to do this operation. Right? If I inserted 1, where would it end up being? Less than 3. And we see, oh, there's a leaf, 1 and 2. It's a 2 node, so it can grow into a 3 node. All right? Let's insert one more thing. Say 5. Where is that going to end up? It's between 3 and 7. So we go down to the middle one. That's a 2 node, so it can expand into a 3 node. All right? One more. How about 10? We insert, and that's greater than 7, but that's a 2 node, so we can expand it out into a 3 node. Now, if I insert one more thing, what's going to happen? This is a completely full tree, right? Every node here is a 3 node. We have maxed this out. If we insert one more element, we necessarily have to increase the height or the depth of the tree. But we also need to make sure that it is still a 2-3 tree. All of the leaves have to be on the same level. I can't just put a leaf down here, for example, right? Because then that would only be one leaf, and then the rest of the leaves are missing. That would be unbalanced. Right? So let's go ahead and insert one more thing here. 6. And let's predict what's going to happen. It's going to be between 3 and 7, so it's going to go down to this middle node right here. 4, 5, 6. That's too full. So 5 gets promoted up, and it gets split out into 2 things. Again, let's go ahead and visualize this over here. So what did we have before? 3 and 7. And then what? 1 and 2. And then over here we had 8 and 10. And then down here we have 4, 5, and 6 temporarily, right? It's too full. We can't do this. So what happens is we take 5 and promote it up. We end up splitting this node again. So temporarily what it looks like is 1, 2, 4, and 6, and 8 and 9, and 8 and 10. In other words, 4 nodes because this middle one was split. And we have 3, 5, and 7 up here temporarily. Can you have 4 children? Nope, that violates the maximum. Can you have 3 keys? Nope. So we continue with our promotion. And we take 5 and promote it up, splitting this node in half. And that leaves us with a visualization that looks like what? 5 at the top, 3 and 7, 1 and 2, 4, 6, and 8 and 10. Everything is a 2 node except for the 2 on the edge, on the bottom, right? And these are all 2 nodes. Oops. There we go. But you see that this split right here, this split resulted in 2 nodes, and they end up on different sides of the tree. Okay? So let's take a look at how this visualization shows it. Promote it up, split everything, and now, again, all the leaves are at the same level. Do we want to see any more? I wonder. I don't even know what this would do if we inserted a duplicate. I don't want to screw it up, but okay. Yeah, ugly. Right? That's why we shouldn't allow duplicates. Because now, if I want to delete 5, which one do you want to delete? All right, I'll delete that bottom one. Let's find out what happens when it deletes the other 5. Basically, it's even more complicated than an AVL tree for deletion, because what you have to do is if I have this gap, I have to borrow a key from one of my children. If one of those children is a 3 node, then it's got a spare key to borrow, right? And it can become a 2 node. But if it's a 2 node and I need to borrow that one key that it has, that means I got to propagate downward for all this stuff. So delete 5. We promote up. Oh, the usual. Okay, there we go. It's the usual. Now let's delete 4. Now we will end up promoting 3. But what happens? This does not. You can't have a gap here. So I'm wondering what. No, I want to delete 4, not insert 4. All right. Let's find out. 3 gets promoted. Yep. So we necessarily collapse the tree that way.
That does sound complicated.
It's complicated, and that's why I don't have you program it. If you really want to see what it looks like in the notes here, I've got at least a half a dozen scenarios. Right, the left sibling can spare a key. B and C are rotated. You can get way more complicated than that. A generalized rotation, B here, if we delete this and we've only got one child here, then B is promoted, F is demoted, E swings over to become F's left child, etc. It can get way, way more complicated. So I've got at least a half a dozen scenarios here that are all mapped out on what would happen if ... Yeah.
Is it still log in? Because it seems like you have to start looking at either side of the tree.
No, it's still log in because you don't have to propagate both ways. I think you only have to propagate to like cousins or siblings, I guess, and then you propagate down one way or the other.
Okay.
Right.
It still seems you're taking either the maximum.
Well, you are doing that, yes, but then you have to fix the tree so that it's still a 2-3 tree, and that's where the borrowing comes from. That's where the swinging comes from. It's stuff like that. Now, B trees are, the generalization of B trees allows you to define M. You don't have to go with 2, you don't have to go with 3, you could go with, say, 20. You could go with 50, right? And now you have an implementation that is commonly used in a lot of databases. Because of that tunable parameter, what you can do is you can tune it exactly for a particular system so that it matches like, say, a page size, right? And then you can minimize cache misses and cache hits in your memory structure. And so that's why it's used in a lot of database systems. B trees are. All right. So let's talk about the mathematics first of all. How do we have a guarantee of the number or the height or the depth of the tree? Right. So what we're going to do is we're going to come up with an upper bound and a lower bound. So let T be a 2-3 tree of depth D. What is the maximum number of nodes of, here I'll say keys in T? What is the minimum number of nodes, keys, in T? So what about the maximum?
3. No, 2. 3 to the D.
Yeah, something like 3 to the D. Let's think about this in terms of an actual tree. So here's a node. It may or may not contain 1 or 2 keys. Here's another node. Well, actually, no. We'll say that it maximizes if every node is a 3 node. right? We're going to shove as many keys into this tree as possible. So let's visualize that. If there are 2 nodes here in the first one, that means that there are 1, 2, 3 children, each with 2 nodes, or each with 2 keys, excuse me. 2. Each one of those has 3 children. Right? Each with 2 nodes, 2 nodes, 2 nodes. Right? So let's just start counting up the number of nodes at each, or number of keys at each level. So here's the level, and this is 0, 1, and 2, 3, ... I won't bother writing the 3, but it is of depth D. Okay? How many keys, number of keys, are there at each one of those levels? So at the first level, it's 2. At the second level, it is 2 plus 2 plus 2, 6. At the level 2, how many are there? I count 9 times 2, right? In fact, I'm going to leave it in that form. And I'm going to go back and change these forms. There's 1 node and 2 keys. There are 2 keys each node, and there are 3 nodes. At level 3, even though I have not drawn it, what would it be? 2 nodes per key, or 2 keys per node, and how many nodes? 27, okay. And then ... 2 keys for each node at level D, and 3 to the D nodes. What is the grand total here? What I'm doing is I'm running I from 0 up to D of 2 times 3 to the D. Pull out that 2 because it doesn't matter. And now you give me a closed form. Oh, sorry. That should be I. Now you give me a closed form solution of that geometric series. Do we remember our geometric series formulas?
Isn't that where it just keeps multiplying?
Well,
It's the sum of the
summation of a geometric series, yes. I starting at 0 up to n of, say, x to the I is equal to x minus 1 in the denominator over x to the n plus 1 minus 1 in the numerator. So my x in this case is 3. So what do I get? 3 to the n, or in this case d, plus 1 minus 1, all over 3 minus 1 is 2. So guess what? Those 2's end up canceling. And what do I have? 3 to the d plus 1 minus 2. Minus 1, excuse me. All right? That's the maximum number of keys in a 2-3 tree of depth D.
Isn't there the x minus, oh yeah, that's 2. Okay, cool.
So is the parentheses supposed to be around the 3 to the d plus 1 minus 1?
Yes.
Okay.
Yep. All right. Let's do all that again, but with the minimum. It is minimized when every node is a 1 node. In other words, you've got a regular binary tree. Right? You've got 1 at level 0, or level 0, you've got 1 node, a key. At level 1, you've got 2 keys, then 4, then 8, then 16, right? It's a binary, it's a base 2 geometric series here. And so at level D, you have 2 to the D keys. Okay? Sum all of those up. And again, using the exact same expression here. When x is 2, though, this disappears entirely. The denominator goes away. And so what are you left with? Sum is going to be 2 to the d plus 1 minus 1. Okay? And there's only 1 key per node, So the number of nodes is equal to the number of keys. So my claim here, what we've just proved, is that let n be the number of keys in a 2-3 tree. We've got an upper bound on n of, what was it again? 3 to the n, or sorry, 3 to the d plus 1 minus 1. And we've got a lower bound of 2 to the d plus 1 minus 1. All right. Now what I need to do is I need to get a hold of d. So I'm going to solve both sides. First of all, I'm going to solve this equation in terms of d, and then I'm going to solve this equation in terms of d. That means that I'll flip those around basically, and the lower bound will give me an upper bound on the depth. The lower bound on the number of keys will give me an upper bound on the depth, and vice versa. Let's take this one first of all. If I solve for d here, what is it going to look like? It's n plus 1 on one side. And then to get rid of that 2 to the d plus 1, it's going to be log base 2. And then to get rid of that plus 1, minus 1. So d is less than or equal to that. Now take this one. And take 1 onto the other side. Log base 3, and then subtract 1 off of that. And you get that this is less than or equal to d. Put these two things together, and you've got a lower bound on d of log base 3 of n plus 1 minus 1, and an upper bound on d of log base 2 of n plus 1 minus 1. Right. You could add 1 to every single side if you want to, but it doesn't really matter. What does this tell you about d? It's going to be theta of what? Log n. Why did I not write the base there? Is it going to be base 2 or is it going to be base 3? Doesn't matter. All logs are the same to within a constant. I could take this lower bound and transform it into a log base 2 and simply just have a constant sitting out front here at the end. All right? It is trapped, the d is trapped from below and it is trapped from above. Therefore, we can say definitively that it's theta log n. That's the cleanest analysis of any of these things. Right? All right. I'll leave that up.
So the base doesn't matter for orders like that?
Exactly, because a log base, all logs are the same to within a constant. Right? We all remember the change of base formula, right? Log base b of x is equal to, if I wanted to change that into log base a of x, what do I need to do? A of b, right? Which is equal to some constant log base a of x. In other words, all logs base b are the same thing as log base a with some stupid constant sitting out in front. This is the change of base formula, right? Right. Okay. So 2-3 trees. Cool. Now, if you go off to Wikipedia and look at balanced binary search trees, you will find that there are no less than a dozen different ones. There are red-black trees, there are splay trees, there are A trees, there are A star trees, whatever. There's like at least a dozen other balanced binary search trees, each of them guaranteeing order log n depth on the tree. Same operations of insertion, searching, and deletion, and they all have different properties. Right? There's an entire series of balanced binary search trees. One reason I don't generally require anybody to implement them is because, one, it's difficult, but two, you usually use what's built in. So Java, what do you think? there is a tree set. What do you think the implementation is? Or does anybody know? It's not something we've talked about here. It's called a red-black tree. And it basically uses the same rotations, left-right rotations, but it also maintains colors of nodes to ensure that the depth is logarithmic. And it is an actual red-black implementation. What about Python? That's a good question. Is there a balanced binary search tree implementation in Python? Does anybody know?
Right with balance of trees? I thought like everything under
Nobody's going to make a binary search tree that's unbalanced, right? That would be wasteful, waste of my time. But balanced binary search trees in Python, let's say 3. I imagine that it's probably going to be in some library, not as part of the standard language. So that's an exercise, exercise, exercise.
Maybe.
Yeah, it's always an exercise. Is there a module for balanced, this is my question. Is there a module for balanced binary search trees in Python standard library? No, there's not a balanced binary search tree in the STD
How
lib.
old is this?
I don't know. 2010? But I can almost guarantee you that no, that it's not. And without looking at the answer, I can tell you why. Because of the next thing we're going to look at, which is even better, right? Hash tables. Right? A dictionary uses a hash function or uses a hash table under the hood. And a hash table is even better. Because whereas a balanced binary search tree, what guarantees do we have now? Balanced BSTs. They offer guaranteed order log n insertion, search, and deletion. Right? Also, the CRUD, create, retrieve, update, destroy, those 4 basic operations on any piece of data. Create is insert, retrieve is search, delete, destroy, delete. We always ignore update. Why?
the same as search.
It's the same as search and delete and insert, right? All 3 of the other ones will go into a combination for the update. Find what you're looking for, change its value, delete it, change its value, and then insert the new value, right? There are probably more efficient ways of doing it in general, but that's the idea. You really only need these 3 operations, okay? So that's order log n, but hashing is even better. Hashing offers the potential for amortized constant time operations. So what is amortization, first of all? Ever do a loan amortization table? Right? I think that's pretty standard, at least in the courses I offer. You do a loan amortization table or a savings amortization table where you look at the total cost of a loan over time. Because at the beginning of the loan, you're paying high levels of interest. You're paying the same percent of interest every single month or year or whatever. But over time, since you're paying down the loan, you don't pay as much interest on the balance anymore. If you start with $10,000 and you pay 5% that first year, you're paying about $50. But in that last year, when you've only got $1,000 and you're paying 5%, or I guess $500, now you're only paying $50, right? So what is the actual cost? Well, the cost goes down each time over the life of the loan. With hashing, hash-based data structures, the cost might spike at certain intervals. But overall, if you look at the overall cost over the lifetime of the algorithm, or the lifetime of the data structure in this case, and you average the cost, then it's actually pretty low, right? Think of it like in terms of you may not be renting yet or buying a house yet, but think of it in terms of this. If you were to rent a house and you only had to pay $5 a month, except that every so often something in the house broke and you were responsible for it rather than the landlord. And so the refrigerator goes out. All right, that's a $2,000 charge, right? Would you take that over something that, I don't know. Would you take that over something where you were paying $500 every month instead? You'd have to do the amortization analysis, right? Over the time, what is the probability that a major appliance will go out and I have to pay for it versus the savings of only $5 a month rent versus a flat rate of $500 a month rent, right? And over time, you have to look at the cost over time, that the average cost, is it higher or lower with option A or option B, right? I don't know, would you?
No.
Well, you would take the flat rent?
Refrigerator breaks every 4 months.
Hopefully not. What kind of refrigerators are you buying that break down every 4 months? Well, anyway, that was a toy example anyway, but you get the idea. That you have to look at the lifetime cost of a data structure, and that's where this amortization comes in. The cost will spike because you have to do what's called rehashing. But the other operations are so cheap at every other interval that it actually comes out to amortized constant time. Finally, what is hashing? I'll give you that as a vocab word over the weekend. Think of hash browns. Everybody's eaten hash browns before, right? I don't know if any of you are in the dorms or not. Do they serve hash browns over there?
Yeah.
Right? What are hash browns? Diced potatoes, right? You've cut them up. That's what hashing is. You hash the potatoes, right, into small little bits. And that's what hash functions are. They are hashing a function domain into little bits. Right? They're cutting up the big potato. Yeah.
So amortize basically means like, I don't know, like roughly, or like sometimes.
You amortize it over the life of the loan, or the life of the rental, or the life of the data structure in this case.